So welcome to this new episode of Story of Photoelectric Effect, and today I'll be talking of another landmark work, and that is by Philipp Lenard. Extremely good experimental physicist, 1886 PhD and Nobel Prize winner of 1905 Physics Nobel Prize, and that was given for his work on cathode rays. And as we had been discussing, this cathode rays was at the center of our story, and essentially, as you know, it's a glass tube in which gas is put or air is put inside at appropriately low pressure. Then you have a cathode, you have an anode, and tens of thousands of volts are applied across them. And then from the cathode something invisible comes out and travels through the tube and falls on the glass of the tube, and where it falls it creates greenish shining, right? So some kind of a phosphorescence is there. Okay, so Lenard also worked on that, and that time, this is 1886, 87, that period, these cathode rays were very well established. Something comes out from the cathode and falls on the glass where it gives that glow. But what that something is a negatively charged, and it can be deflected by magnetic fields and electric fields. All those things were there, but whether they are material particle, mass is there, or it is some kind of just like say ultraviolet radiation. Okay, so that is also invisible. You don't see ultraviolet, but then yes, it is emitted and it goes and it falls and it does some tricks. So that was a kind of confusion. Some scientists believed that it is some kind of a wave in that hypothetical medium ether, which was supposed to be there everywhere in all materials, all transparent materials, and everywhere in space, and so on and so forth. So just like electromagnetic radiation, this is also some kind of a radiation. And another set of physicists thought that no, these are material particles which are ejected from the cathode, and therefore they are constituents of matter. Now, 1888, Lenard created a tube, fabricated a vacuum tube, to see if these cathode rays can pass through quartz. Why quartz? We had already discussed that quartz allows UV light to go through. Okay, normal glass doesn't. So these cathode rays were not coming out of the normal glass. Outside that vacuum tube, you put anything, it won't glow. So if it is that kind of radiation, UV kind of wave in the empty space, then it should come out of quartz. So he tried that, did not succeed. In 1892, he joined Heinrich Hertz as an assistant. Right, 86 PhD, he did some job here and there and there and there, and then for 2 years he was at Bonn as an assistant to Hertz, and there Hertz showed a discovery or a result that he obtained from his experiments on cathode rays. And what was that? What was that? Suppose you have a vacuum tube, just a schematic design. You have a cathode here. Let us say you have an anode of this kind. This is an anode, a plate with a hole, right? A plate with a hole. Of course, it won't come out. So this is, let us say, this is the anode, and then this is connected to cathode, and anode are connected to that high voltage and high voltage. And then the cathode rays will come like this. Now, what Hertz was doing was trying to study the effect of this cathode rays on different materials. So one material was uranium glass. right? Uranium glass. It's some kind of glassy structure in which uranium oxide is embedded in some form, and if you put that material in the vacuum tube, inside this vacuum tube, then this glows. Then this glows. So if cathode rays falls on this, it glows, right? So doing an experiment on cathode ray inside this vacuum tube was quite difficult, because there are so many constraints. You have vacuum, you have gas at certain pressure, and then you have high voltage there, and you cannot do much here. But still, people were doing experiments. Now what Hertz had found, which he showed to this Lenard, that if this uranium glass tube is wrapped in an aluminium cover, okay, suppose it is wrapped in some aluminium foil inside this uranium oxide, and then if he puts it here, then he finds that this uranium glass still glows. Okay, still it glows inside that cover, and that means the cathode rays are penetrating this aluminium and then falling on this uranium. So that was something very new, that cathode rays can penetrate through aluminium foils. So Lenard picked this up, right? After discussion with Hertz, Lenard picked it, and then he was very excited to take this cathode rays out of this cathode ray tubes, right? So what he did is that he put an aluminium window here, okay, aluminium window here of appropriate thickness. Appropriate thickness, why? Because inside it is vacuum. Vacuum means low pressure. Outside it is atmospheric pressure. So if it is too thin, that pressure difference it will not be able to tolerate and will get punctured. And if it is too thick, then the cathode rays will not come out. So appropriate thickness of aluminium window, and from here, when he puts some fluorescence material somewhere here, then he finds that yes, it glows. That means the cathode rays are coming out. And not only that, if he puts this this material at some distance also, then also it glows. That means after coming out, it travels. And Lenard had done a very systematic study of these cathode rays which are going in air, at atmospheric pressure. Right? Here it was at a very low pressure, and now here at normal atmospheric pressure it is coming. And he had made several studies on that. And I will show you the pictures which are there in his Nobel lecture, and tell what kind of studies he has made on these cathode rays. So this is that Lenard's vacuum tube which he has used extensively. On the right hand side you have this cathode and anode. That A is written for anode. It's a kind of a hollow cylindrical thing from which this cathode thing is going, and then the cathode rays are coming. On the left you have that window, aluminium window, from where the cathode rays are coming out of this vacuum tube, and these cathode rays in that so-called observers rooms are being studied. So it was like a regular tube with some construction. So suppose this is that regular tube, and then the cathode was like this rod kind of thing, and here you had seen C, and this A was some kind of hollow cylindrical metallic thing, and from that hollow part this was going, and this was anode, and of course the pumping and all those things will be there. Regular ways to produce cathode rays, and on the other side you have this aluminium. This part is aluminium. Remaining is glass. Remaining is all glass. So cathode rays which come from this cathode, they pass through this aluminium and then come out. So the first thing he did was that test material which glows, some kind of phosphorescence. So that he put outside here and finds that yes, it glows, and then he takes it away and finds that up to some 8 centimeters the glow was there, right? So the cathode rays at one atmospheric pressure could go up to 8 centimeters or so. So this is the kind of thing. So this is this material. Then he studied varieties of things. Once the cathode rays are here, then he can study varieties of things. He gives the simile that suppose you have a furnace and that furnace produces light, but if that light cannot be taken out of that furnace, if light is always inside that furnace, that's the only place where you see the light, that furnace, then you cannot do many experiments of optics. Optics could not have developed. Since light can be taken out and you can do in your laboratory varieties of things with that light, therefore so much of optics is developed. Similarly, once the cathode rays are out of that source, where you have all varieties of complications, 30,000 volts and all those things, once it is out of all that complications, then you can study it very well. So first thing it studies is that when it comes in air, then not only that it is gradually absorbed, it also scatters. So that was the first study, it scatters. And there are a lot of physics he has derived from there, that light can go through air so well, and these particles are getting scattered. Light cannot go through, let us say, milk, because milk is turbid. All those fat particles are there, and light, when hits those fat particles, then it scatters. But on the molecules, on air molecules, the light just goes through. But these cathode rays are scattered, they become diffused. That shows that these cathode rays have some structures which is much more minute than light, and must be smaller than the size of the molecules of air, and therefore very tiny, at least 1000 times smaller. All those things he concludes from that scattering of these cathode rays in air itself. And to show this turbidity or this scattering or this diffused kind of thing, he makes another apparatus which I will show you on the screen. So in this diagram, the cathode ray tube is to the left of this whole diagram, and the cathode rays coming from left out of that aluminum window, going through the slit on the left. And then these cathode rays are falling on a screen. That bigger line that you see is the edge of the screen, and that fluorescence in screen is in the plane of this diagram, this whole plane. So maybe I will explain it better on the board. Just to keep this diagram in mind, and we will discuss on the board. So in this screen you have a slit here, and the cathode ray tube is on the left, and here is that aluminum window, and then the cathode rays are coming through the slit, and then here he puts the screen in this plane itself, like this. This edge of the screen is here in front of this, so this is all glowing. And then on this, what kind of thing is observed, that is important. So you see that it diffuses like this. And next thing that is there that he has studied is absorption by different materials. So there the arrangement is like you have you have a screen here. Let us say you have a screen here, and then parallel to this, between this screen and the cathode rays which are coming, you put another material parallel to that, and then this material, this is the absorbing material, and different thicknesses, different kinds of materials he puts here, and then sees what happens to this, right? So this is let's say that material in between. Here is that screen on which this cathode rays will make marks, and the portions where cathode rays will come, that will glow, and from here the cathode rays are coming. So varieties of materials he has put here, and then he has seen whether it is absorbing and it still remains dark, or portions are glowing, and so on. So you first see the original things, and then maybe we can discuss. So this is another photograph from Lenard's Nobel lecture, and here you can see this screen on which cathode rays are falling, but in between the window of that cathode ray tube and this screen, they put a material. The upper half, which is almost black, completely black in fact, that corresponds to a 0.5 millimeter thick quartz plate which is placed between the cathode rays and the screen, and the lower half where you see a lot of this glow, there a thin aluminum foil is placed between this window and this. So the idea is to see what kind of material, of what thickness allow this cathode ray to go through and what stops. So this kind of studies are there. So what you have seen, if you see this in this orientation, then this part was dark, and for this part, this was quartz plate. Okay, for this portion, it was a quartz plate of some 0.5 millimeter of thickness. This was, and for this part, it was aluminium, thin aluminium foil. So varieties of materials he has studied, and very interesting result he has found, that the pattern of absorption, what will absorb and what will transmit and how much it will transmit, that does not depend on the chemical composition of the material in the first approximation. In the first look, it appears that that chemical composition has nothing to do with it. It's only how much material is there, how much weight per or how much mass per unit area of that absorbing material is there. Only that decides whether it is how much it will absorb and how much it will transmit. From this, he discusses a lot of things about the atomic structure, and comes out with beautiful models which finally could not sustain, but very thought-provoking and very interesting models he has devised. And one of the things that he has concluded from this is any atom of the material has a lot of empty space in it. So from Rutherford model, we know that yes, inside the atom we have a lot of space, but from these experiments also he has concluded from all this scattering and absorption that atoms must have a lot of empty space, and the actual material should occupy only a small volume. And based on other things, he comes out with a thought model, and that model is also very interesting, and it's like this. This is atom. Then he says that okay, the atoms are made of small dipoles, plus charge and minus charge, tiny plus charge, tiny minus charge. So plus charge and minus charge together. And these kind of structures are there. Okay, these kind of structures are there, and there are a lot of empty space. A lot of empty space. There are some these things, and then there's a lot of empty space, and the atom as whole is of course neutral, and so on and so forth. So these are the kind of things, many things he has done, but not diverting too much in the other things that Lenard did. We will talk of his work on photoelectric effect.